This is the remainder of some of the radical problems that we were doing today in 1.2. Just skipping on down to example number 1. Depending on which class you were in, I either did B or C, so I'm going to rework both of those really quick just to make sure each group has it. So this is example 1 in the 1.2 radical packet. So looking at part B, you're looking for perfect cubes that make 16, x cubed, y eighth, and z to the fourth. I like to think of that as what's the perfect cube I know that goes into 16. Well, if you think of your factors of 16, excuse me, 4 and 4. Per perfect cubes, 8 would be the biggest perfect cube that goes into that, so we would break this into the cubed root of 8 times the cubed root of 2, because that makes 16. Then we would also think about our variables, cubed root of x cubed, cubed root of y to the 8th, and cubed root of z to the 4th. Cubed root of 8 is 2. You can't do anything with the cubed root of 2 because that doesn't have any perfect cubes in it. If you have a number that matches inside and outside the power and the root, that just gives you x. If it's bigger inside, then you have to ask yourself, how many times does 3 go into 8 equally? That goes in twice, so 2 groups of 3, that would make 6, with 2 left over. And then 3 goes into 4 once, so there'll be a z to the first on the outside with 1 left over. So our final answer for this one is we bring everything that's outside, so the 2, the x, the y squared, and the z, and then everything that's in the cubed root stays in one big cube root, so a 2, a y squared, and a z. So that is our final answer for part B. For part C, you probably want to put these together first. So 3 times 6 is 18. A squared times a to the 5th is a to the 7th. B to the 3rd times b to the 1st is b to the 4th. We're doing a square root, so perfect squares that go into 18. The biggest one I can think of is 9. And 9 times 2 makes 18. We also need to think about the square root of 7 and the square root of b to the 4th. Square root of 9 is 3. You can't take the square root of 2. This is, remember, a square root, so 2 goes into 7 3 times exactly with 1 left over, so that's the part that's inside the radical. This is 2, and 2 goes into 4 exactly twice. There won't be any more radicals for the b. So the outside parts are a 3, an a cubed, and a b squared. The parts left inside are a 2 and an a. So that radical has also now been reduced. Moving on to example 2. These are the ones that I said you have to be careful with when they want you to talk about absolute values. If they ever tell you that you don't know if your variables are positive or negative, then anytime it's an even root, any variable that you pull out will need to put in an absolute value. If it's odd, it doesn't matter. You just do it normal. So for this even root, first of all, we need to know what's a perfect fourth for 81. So think about your factors of 81. 1 and 81. 2 doesn't go. 3. Let's see, 3 goes in 27 times. 4 doesn't go in. 5 doesn't go in. 6 doesn't go in. 7 does not divide into 81, I don't believe. No. 8 doesn't go in, and then you have 9 times 9. So actually, 81 is a perfect fourth because 9 times 9 is a 3, 3, and a 3, 3. So 3 to the 4th actually is 81. Sorry, it's really late. So this one actually is a perfect fourth for that. So that would come out as a 3. When we do our variables, think about those separately. For the r, you have 4, you're doing the 4th root, so one group of 4, so you're going to pull out an r. Because we don't know the sign of the r, we're going to put it in an absolute value. And we're also going to have an r left over in the radical. For the s, you have 4 goes into 8 exactly twice, so we would normally put that in its own absolute value. Now the only thing is, if it's squared, or to the 4th power, or to the 6th power, Technically, you don't need an absolute value because it's going to be forced to be positive. So the technical right answer is to just leave that as s squared. If you leave it in the absolute value, that's fine. You could also write this as 3rs squared in the absolute value. Keep it all in the same absolute value. All right, for this one we shouldn't need to do anything with absolute values because this is an odd root. So the cubed root of 8 is 2. It's a perfect cube. 3 goes into 6 exactly 2 times, so that means there's 2 groups of 3 in the A's. 3 goes into 3 once, so everything actually comes out of the radical in this one. Okay, we did a couple of the rationalizing problems in class. I'm going to do the ones that we skipped over. So we need to start off with C. Excuse me. So we have, I always like to split this. This is square root of 2 over square root of 3. To get a perfect square in the denominator, you need to multiply by another square root of 3. So that would make this square root of 6 over square root of 9. And the square root of 9 is 3. You do need to make sure that the top radical is reduced, but no perfect squares go into 6. Okay, let's look at example D. Be careful here, this is different than any that we've done before. This is a fifth root. So split it on top and bottom as a fifth root. So you have to ask yourself how many more y's do you need to make appear so that you have a group of 5. We would need 3 more, because that would be 2 plus 3 more would make 5. Whatever you multiply by on the bottom, you have to do on the top. So this becomes the fifth root of xy cubed. You just put those two together over the fifth root of y to the fifth, and the y to the fifth would just become, fifth root of that would just become y. So we've gotten the radical out of the denominator. And then we want to do f. So f is, I would worry about that negative exponent first. I would rewrite this as a 16 and an a to the 8th on top and a square root of b squared on the bottom. Square root of 16 is 4. 2 goes into 8 exactly 4 times, and square root of b squared is just b. So that's how that one works out. The last piece that I want to do before I finish the notes for tonight, and like I said, we would pick up with the rational exponents next time together. There's not that much left on that. But I want to talk about rationalizing a denominator that has 2 terms in the bottom. So notice that this is a square root of t plus a 4. You can't just multiply by square root of t across the bottom because it would get rid of the first one, but it would create a square root on the second term. So the only way to do a binomial and get rid of a radical in a binomial is to use something called the conjugate. The conjugate just means the sign in the middle changes. And the way that works is it gives you actually a difference of 2 perfect squares that when you multiply out. So, keeps wanting to go up too far, sorry. If you look at this one, the conjugate of my denominator is I take the same denominator and I only change the sign in the middle. So these two are conjugates of each other. Whatever I multiply on the bottom, I have to multiply on the top. So now here we're going to FOIL this out. So square root of t times square root of t would be square root of t squared. Square root of t times negative 4. Those don't go together because one's inside and one's outside. Excuse me, sorry. Then we would do negative square root of, or excuse me, negative 4 times square root of t. And then negative 4 times negative 4. So that completes my top. I'll worry about simplifying it in just a minute. On the bottom you get square root of t times square root of t, so that's square root of t squared. Square root of t times negative 4. 4 times square root of t. And 4 times negative 4, so that's negative 16. Notice on the bottom, like terms are canceling, but they don't on the top. The square root of t squared is just t. This would be negative 8 on the square root of t, and then plus 16. The denominator is square root of t squared is just t, and then you have the minus 16. Now you cannot cancel anything because these all are separated by plus or minus, but you no longer have a radical in your denominator. Okay, so we'll pick up on class time on Wednesday with the rational exponents, and I will see you then.